Hi everyone. Today I'm going to talk about my work on using multimodal information to help machine to acquire different type of abilities. My name is Zhou. I'm from University of California, Davis. In my lab, we have various different types of work that are related to multimodal information. One of them is called multimodal translation. So, a lot of times when we talk about translation, we are always thinking about converting one language to another. But sometimes, if we have other information, such as multimodal information as vision, we can utilize that information to improve machine translation. For example, you have a real application that you're an online company, you're selling different products. Originally, where all the descriptions were written in English, but now you're expanding your business to another country. They speak a different language, so you need to translate it to a different language. With the image, for example, your product image as a condition during translation, your translation will be more accurate. For example, certain multi-sense words and nouns, such as buy, can be translated in various different nouns in other languages, which is ambiguous by definition in English. You can resolve these issues with extra information of images. Another type of applications we looked at is about social media related information verification. If you have right now Twitter or Facebook or Google News, they always sometimes have images correspond or co-occur with the text. You can utilize informations such as inverse image search to find all articles containing similar images to help you to ground to see what if the images were used in one previous event and right now was borrowed for manipulating information to create fake news on current events. So these information of we also call it trying to figure out if using different type of information to expand your current database to help you to gather more information for verifications. Conversational system could also be used as intelligent tutoring system. We have a collaborative work with Educational Testing Service, ETS, on how to build training systems for people to train on different abilities. So here is a second language training system. A user is going to go through a job interview setting with a conversational agent, so he can learn to get used to how to express his experience in English, which was his second language at this particular application. And then we're going to utilize the multimodal information we gather from the interview and give him some suggestions for adjustment. We're also going to do real-time interactions by tracking his eye gazes, tracking his voice intensity, and maybe encourage him throughout the conversation when some of these informations indicate that he's not engaged or not confident. Similarly, we could also apply conversational system that was multimodal ability to health domains so that we can particularly interact with patients to gather information from them. So this is a project which is a collaboration from University of Southern California of having this LE as a conduct a semi-structured conversation with the patient to screen if he has mental disorders such as depression or PTSD. Today, we're going to focus on three applications that utilize multimodal information. First is that we can talk about how do we infuse multimodal information to enable a system to have situational awareness. The second one is how multimodal information to help your system to make better decisions. And finally, how multimodal information together with text information can enable better communication between machines and humans. First, When we talk about situation awareness, situation is kind of really broad. We're talking about the real-time environment that we're in. What's the time, who are we interacting with, what's the temperature, what's the sunlight. All these informations are situation. A system cannot track everything. So here we're only tracking on important information that are critical to the task. Particularly, we have a task here, which is a customer service environment setting that the system is going to give people directions to different offices. Here, we really wanted to make sure the user is having attention on the robot when we deliver instructional information, because lack of attention in critical information delivering can result to really bad task completion. So how do we detect users' attention? Here, we're mostly defining user attention as the visual focus of the user. Um, we're going to use two types of information to help us to get a robust attention detector. For example, we're going to use a head tracker to track people's head movements so that we know which direction the head or face is facing in order to infer users' intention. The other is voice direction. Since we have a microphone array on top of the robot, so we can use the difference between the voice, the different time that the lags of the voice reaching different microphones to calculate the voice direction of the user. So these two types of information coming from different sources can help each other to make sure that we have a robust attention detector. Because a lot of times with really bright lightings, head tracker can fail. With noises of the elevators or people crowds, the voice voice direction detector can fail. So with the two type of information added together, we can be more robust. Now, we thought we were going to have everything, but still, here is an example of a problematic real action.
Do you need directions? Sorry, say that again.
I'm looking for my meeting.
You said Matt McGinley, right?
No, give me a minute.
Sorry, that was Alberto Bacala you wanted, correct?
That's really long. Bye.
Well, yes, I'll see you later.
So here we see that the user was trying to look at her phone to find the room that she wants to go. But the robot doesn't understand that the user's attention was not on him. He kept prompting to find a user's name based on what the user find a name the user wants to get access to. But this is sort of a problem that we find. A lack of attention can really disrupt the interaction. So can the robot obtain users' attention during the interaction? There are different ways that we can gather such attention. So we find in human conversations, people sometimes use disfluencies to calibrate each other's attention. So here are some examples by Charles Goodwin. He found that in human-human interactions, you may have not noticed that, but when you really think back, that we actually do that a lot. For example, here, Barbara and Brian. Barbara is the speaker. He's saying, Brian, you don't have your kids that have to go. So she had the disfluency, which is a self-correction in the middle, which attracts Brian's gaze. Brian wasn't originally looking at Barbara, but he hears something like a disruptive in the middle, which actually attracts the user's attention. So here we're saying that disfluencies are not mere cognitive generation error. Sometimes it was also used as strategies to attract each other's attention. You may not realize that you're doing that all the time, but this is not, a lot of time it's subconscious that you're using the strategies. So we are gonna make the robot do similar things. So we designed several attention coordination strategies, such as we're gonna have pauses, we have interjections, such as excuse me, we have restarts, such as say two words and say that again to get to 3800. You also have repeat phrases. And based on the conversational situation of user attention, we're gonna apply different strategies at runtime. So here is an example conversation that we have.
You need help finding something?
Yes.
Could you tell me the room number or person you're looking for?
I think it's 4800.
To get to 4800,
No, I think it's 4300. 4300, yeah.
excuse me,
4300.
go along that hallway.
I'm looking for 4300.
4300 is just down that hallway and will be the first room on your left.
Okay.
By the way, would you mind swiping your badge on the reader below so I know who I've been talking with? Can I help you find something else?
No, I think that's it. Thank you. Bye-bye.
Okay.
Bye.
Bye-bye.
So this is the conversation, the same interaction where the robots view.
It's 4800.
To get to 4800.
So here, the robots detected that the user is lack of attention based on the signals that we provide.
Excuse me.
Then he said, "Excuse me," to attract attention. But still, we didn't get users' attention back. So the next strategy plan was to do restarts.
Go along that hallway.
I'm looking for.
So now, after we said go along the hallway, we successfully reobtained the user's attention.
4300 is just down that hallway and will be the first room on your left.
So here are some other natural interactions with real users interacting with the chatbot.
To get to 2801, take the elevator down to the second floor. Turn left as you walk out of the elevator and continue on to the end of that hallway. Excuse me. 2801 will be on that side of the building.
Excuse me. Can I help you find something? Warning. Do you need directions? Excuse me. Do you need directions?
How to get to 2224.
So here we see that the interjections or restarts or repeats are pretty natural. People actually do interact with human beings similar as when they interact with robots. We did obtain the similar interaction results by using a robot. So one of the takeaway is multimodal information, vision, and audio together can be more robust in detecting situational awareness. Subtle language changes do matter in coordinating attention. Second task we're going to talk about is decision making. We know there is a famous game called a 20-question game. We have a visual analog of 20-question game, so that we want the robot to be the guesser, so he can either ask questions or make a guess on images. While here the questions can be a little bit more raw, can be either yes or no questions or asking for an entity of adjectives. So you can think about these tasks could be extrapolated to online shopping conditions. So you have a dish in mind. The robot is trying to help you, given the catalog of menus that he has, which one to sort of recommend to retrieve it for you. It could be similar for clothes or other products. So since that we have the setting, which is kind of very constrained, we can have a nice simulated environment so that we can train the system to make good decisions. We have the setting that we can have a real user to answer questions from the chatbot, but we can also build an automated agent, an answer bot, which you can think about as a visual question answering system to answer questions for the bot. So we can actually use that to simulate the entire action, which is you reduce the number of human input that you need. So we designed the game such as it will terminate in 3 conditions. Either of the three conditions reached, we're going to terminate the interaction. The first one, if the bot guesses the correct answer, basically you win. The bot wins. The maximum number of guesses is reached. You can only guess 3 times. The maximum number of dialogue turns you reach. So in total actions that you can do, sometimes you can do 10 or sometimes you can set it 20. So we also designed the reward that if you win it, you get 10 points. If you lose a game, you get -10. If you make a wrong guess, you get a -3 in points. So this now is a perfect simulated setting that we can test our reinforcement learning algorithm to obtain optimal decision-making process. So we particularly design a hierarchical reinforcement learning algorithm for this task because you can think about the task can be separated into 2 subtasks. You can either ask a question to gain more information at a certain time, or you can make a guess to say, oh, is this the image that you want? So that you can reach the success in the. But if you ask a question, you wanted to ask yourself which question are you going to ask so that you can gain more information to help you differentiate different images in the catalogs. So you can really think about it as a hierarchical decision process. So we also make the system to incorporate that human decision sort of intuition. And then one of the important part of reinforcement learning is really about state. How do you design the state that can capture the most effective information throughout the conversation? And the context of the task is really important. So we have three types of information we track in the dialog state here. The visual belief state, which is accumulated information we have so far about the image that we're guessing. So you can think about it's an imagined image that you have so far. Then the visual context state, which is basically you have a catalog of images. Maybe we say 20. And we wanted to calculate how close your imagined image to that 20 images. So originally, when you have very little information, then you can think about this cosine distance between these 20 images are very similar. So you have a very flat distribution. Once we ask more questions, we get more information about the targeted image, then your distribution is going to be peaky so that you can actually utilize this information to gain sort of insights to make guesses with more confidence. The last type of information we wanted to remember is from history. How many images we guessed so far, how many questions we asked. So whenever we make too many guesses, we want to be more conservative so that we don't fail the task in the end. When we wanted to accumulate information, we have the problem that we are getting information in text, but the catalogs we have are images. How can we map them together so that we know the imagined image that we get from text is similar to the catalogs? So we first need to build a mutual embedding space between image and languages so that we are confident whenever we get more textual information, we can lay top on the imagined image that we have to gain better representation. So to train this sort of a joint space, we're going to do similar things as any pre-training multimodal task. We're going to take existing conversational data that has images. So the visual dialogue, particular, we have an image and we have its corresponding captions and a question-answer pair with respect to this particular image. So we want to make sure these corresponding pairs have a similar distance when they are projected to the embedding space, the joint embedding. While if an image and a caption of a different image, we want to make sure they're far away from each other. So that using these contracted left, we can train embedding to make sure that the image and language can be projected to the same embedding space and do computation over that space. So whenever a new question-answer pair came, it will go through this network and lay out on the existing image, existing representation that we have. Now, after we obtain the information from the state, now we wanted to make a decision whether to ask a question or guess an image, which is the higher level decision. We're going to use a double DQN to do this because we only have 2 decisions So double DQing is the perfect choice. Then when we decide we need to ask a question, then we need to select which question to ask. Suppose that we ask human to help us to write down 20 or 100 questions that are related to the task. Then we're going to pick which question to ask. So that depends on the context that we have, right? So particularly the visual context, the distribution that we just talked about. If we are pretty flat, we wanted to ask a question so that it can differentiate, make it more peaky. So we always wanted to select the question. After asking this question, we're going to get more information. So based on that, we're going to use a DRRN, a deep reinforcement relevance network, to help us to decide which question to ask based on the previous training data. Finally, now we're ready to perform the task after using around 10,000 of simulation to get the perfect model. So you can think about it. At first, you only get the caption of the image as the initialization, but you convert that caption into a joint embedding space. So that's your visual belief state. That's your imagined image. And then you compute the visual context, how far away this particular imagined image to all the candidate images that you have. And then you have your dialogue meta information. You ask no question, you made no guess, and the previous acts are none. And then based on that information, you're going to make the first decision. Since you have very few information, your distribution is quite flat, you're going to ask a question probably at the moment. And then you're going to ask a particular question that can make your distribution more peaky. You're probably going to ask a question that can increase the entropy of your distribution, which means that make the distribution more peaky by deleting probably half of the images that, or like reducing the half of the images that are in semantic space. And then you're going to keep doing that. If you ask a question, that the simulator is going to give you an answer. The simulator here is also another chatbot. He's going to, based on the image that he has, to respond to that question, so he can make errors. So then you're going to take that information and put that into your visual belief state. So you have an extra question answer pair, which is your extra information, addition to the caption. You're going to update your visual belief state. Your imagined image is going to be closer to your targeted image, right? And then you recompute a visual context state. So now your distribution get a little bit more peaky. Your dialogue meta information is going to update it in terms you just asked a question, and your previous action is an ask a question. Now that you go down again to your high level decision, maybe you're good enough. For example, your visual context is really peaky. One of the images that stand out, everybody else is really low. Then you can make a guess. Then you're going to guess, hey, this is an image. If that's correct, then the simulator is going to tell you you win the competition. If you did not guess it right, then the simulator is going to give you deduct you 3 points as a reward failure. But you can take that into your dialogue meta information and then make sure that this one image we're never going to select again, and you want to readjust your distribution. So overall, finally, you're going to reach it until you get the correct answer, or you guessed too many times, or you asked too many questions. In the end, reach the maximum number of turns. Now we're going to test the RS system that has this kind of hierarchical decision process against with other conversational policy that do not have these kind of hierarchical decision. With the hierarchical decision, going to help us. So we're going to do random selection, any question or any answer, or any guesses, or you can make DQA to help you to decide whether to ask a question or make a guess, but you randomly select a question. So we can see with the 20 round, we can do pretty good. We can win 67.3% of the games with 16.68 average turns, while the other two methods are doing much worse. So here is an example, because on the left, you have these kind of different images, and the one that would on the top right, top left is the targeted image that the answer bot has. So the agent is going to select among questions that previously human written, which is from the visual dialogue. So he is going to first pick the question, are there leaves on the tree? And the user, which is an answer bot, is going to say no. what color are the birds? The answer was the red, which is actually a wrong answer because there are other colors, right? And then the agent say both are the same colors. Yes. The agent make the guess, which is the third image on the second row, which is here, but it is according to all the information that was given, he made this choice. And then, but the agent is going to tell him that's wrong guess. Okay, so the agent is going to try to ask a different question here. Do they have any yellow colored feather? No, that's actually a wrong answer again. Do they have any green colored feathers? Yes. Can you see any other birds? No. And the agent made the get the first image on the first row, which is correct at the moment. So which is really interesting to see that the agent can recover from wrong information it was given. It is really hard for a human to do that. But in agent's mind, everything is probabilistic. He's trying to adjust its distribution in visual context state in order to find the correct answer. One problem that we have here is we ask human to pre-written questions and then select questions, which is not very ideal. Because if we change all the images, then we need to ask human to rewrite the questions again, which is not very useful. So if we wanted to make it useful in practical scenarios, we need the agent to ask questions themselves. So instead of selecting questions, we made the agent to generate questions. But the problem is agent would generate pretty bad questions for such as, can you see any people? Is this in the tree? Is it daytime? What color is the sky? Which is not very helpful in differentiating which image is the target image. So what's the problem here? Before we go on to the next task in solving this problem, we wanted to summarize here that hierarchical task structure is really useful in making decisions. Giving the machine certain human intuition can really help it to converge faster and make better decisions. This is sort of an interesting task we can extrapolate later for real practical applications. So finally, we wanted to come into the last tag, which is focus on communication. You not only need to learn how to make decisions, but you need to communicate your decision with human and gather information from human with natural language that is good enough so that you can make a final decision or collaborate with human beings. So we're going to tackle the information problem of text degeneration on the right. So we proposed a alternate training framework, which is a trick that we apply for these type of tasks that you need to make decisions and generate text at the same time. As we know, generating text information, usually MLE-based methods, cross-entropy-based method, is very useful because it could keep a good language model. And pre-training language models are all trained with MLE loss. You can leverage pre-training models that way too. So here, we use supervised learning methods to train the natural language generator. And then we also use a reinforcement learning enabled methods to train the decision maker to guess which images. So here, sort of, what we do is we do the first iteration, we train the language generator. The second iteration, we're going to train the decision maker. And then the third iteration, we go back to supervise the machine generation trainer. And fourth iteration, we go back to the decision maker. So you iteratively alternate the supervised learning and alternate and the reinforcement learning decision making, so that you you not only get to a pretty good decision in the end, but you also generate good questions to elicit useful information from a human. So what we can do, see as here is an example evaluation task we have. So we have the system trained, and then we randomly pick an image. And so the user, the mechanical Turker, is going to see the blue box here. You see a target image, and you can reply questions to the system. Well, the system see all the catalogs on the right, which is like around 10 images. So first, the user is going to give a caption of the images that he saw. He said, a person skied down a slope of snow. Then the agent needs to generate questions related to the task in order to differentiate the catalog images to find the target one. So he looked at all the images and trying to find he needs to ask a question can differentiate from these images. So he first finds, oh, there are different people, different number of people in this. Let's ask how many people are there. You said there's one person. Okay, so it's one person, so you can eliminate this one, probably this one, because there's no people, 3 people, no people. So probably you have 1, 2, 3, 4, 5 less. Then among these 4, you need to ask another question to differentiate it. So the system will come out male or female, which is normally what people would say as well. They say, I think he's male. So you get rid of this one, clear it's a female. The rest of it you cannot tell. And then he is asking details to differentiate this 1, 2, 3. He's asking if he is wearing ski gear. And then he say, yes, he is. So you get rid of this one. You probably have 1, 2. Then is he wearing goggles? This one seems to wear a goggle. This one doesn't. And then he say, and then you guess this particular image and you get the correct answer. So our model does pretty well compared to just doing supervised learning or just doing RL. So we can win the game 67.5% of the time. We also ask the user to rate our interaction if the system is being fluent, being relevant, asking relevant questions. Are the questions easy to comprehend? Are all the questions we ask have diversity? We do better than compared to the other methods, the baselines. And here we're given the ground truth of the caption, so which is from the COCO images dataset. If we ask the user to generate caption, they're going to generate more informal captions, which is different from the training data that we have, which made all the other baseline models do much worse. But our method, since it's iteratively trained, it is doing pretty well and pretty robust. So one of the takeaway we have for here is doing alternate supervised training and reinforcement learning can do pretty well in these kind of decision and communication joint optimized task. Finally, I wanted to say, using multimodal information, you can enable different abilities in conversational system or other in general machine intelligence. We're just talking about various algorithms to make human and machine collaborate better. So finally, I wanted to just mention one of the tasks that we just submitted to a recent conferences. It's called a GanDraw. You wanted to see, previously we always are talking about visual dialogues or visual 20 question games are things that we do to retrieve existing images. But what if we want to generate images from conversations? So here we recruited 2 people to play a game. So the teller is going to see the real image and describe it, and the drawer can interact with the teller visually in language to ask him verification questions and give him clarification questions and acknowledge jobs finished or not. And then he use a tool similar to Paint that paint all the visual semantics on the canvas. And then we use a GAN to convert that semantic map into a more realistic image so that the teller can look at the realistic image and give more instructions. So throughout this process, we generated pretty realistic images of scenes. We wanted to, the goal of the task is really to create a good corpus for us to really study how do we do iterative image generation, how do we do iterative image grounding. So this is a data set we're going to release soon, and hopefully the visual dialogue, multimodal domain researchers will be taking an interest in this. Thank you, everyone.